Hello friends, welcome back to my channel Behind the Truth. Please subscribe, like and share. Let's come to the point. The concept of time is essential for understanding our environment. It allows us to measure changes in objects and their movement. Initially, it may appear that time is absolute, with one universal clock for everything. However, the reality is more complex. In our daily lives, we follow schedules, like starting work at 9 a.m. and finishing at 5 p.m. Our perception of time remains relatively constant during these hours, but it might feel like it slows down as we approach the weekend. However, in the early 20th century, a groundbreaking discovery shattered our belief in the absolute nature of time. It was revealed that time is not fixed, but rather relative. Time dilation is a fascinating concept arising from Einstein's theory of relativity. It involves clocks on different trajectories across space, which were once synchronized but later show different times when they meet again. Time dilation occurs when an observer is moving relative to another observer or when they are in different positions within a gravitational field. This phenomenon demonstrates that time is relative, which may seem absurd but is a fundamental aspect of Einstein's theory. We are familiar with the idea of relative speed in everyday life, such as how a car traveling at 60 miles per hour 97 kilometers per hour relative to a stationary observer would appear to move at 120 miles per hour 193 kilometers per hour to another motorist moving in the opposite direction at the same speed. Similarly, time can be affected by this relative motion. Time dilation, a consequence of Einstein's relativity, causes time to pass at different rates for observers based on their relative speed or position within a gravitational field. Although this effect is usually subtle, it becomes noticeable under specific circumstances. The foundation of Einstein's theory was the constancy of the speed of light regardless of an observer's motion. This led to the conclusion that moving clocks run slower, which is commonly referred to as time dilation. However, this term might be misleading as it focuses excessively on clocks, which are simply tools we use to measure time. Time dilation should be perceived not merely as a clock property but as a surprising aspect of space and time. The theory of relativity consists of special relativity and general relativity, and time dilation plays a role in both. The fundamental principle of special relativity is that the speed of light remains the same for all observers. As explained by physicist Andrew Duffy from Boston University, one consequence of this principle is that two observers, moving at constant speeds relative to each other, will measure different times between the same events. However, this effect is only noticeable at speeds approaching the speed of light. After introducing special relativity, Einstein further developed his theory to include gravitational effects in general relativity. In this hypothesis, time dilation depends on the strength of the local gravitational field, not the speed of travel. As we reside on Earth's surface, we are already experiencing time dilation, thanks to the modest gravitational field here. Moreover, the strength of this effect changes as we move up and down within Earth's gravitational field. The gravitational force weakens on the top floor of a tall building compared to the ground floor, resulting in a milder time dilation effect at higher altitudes. Consequently, the passage of time is faster the further you are from Earth's surface. While this time difference is too subtle for humans to perceive, it can be measured using exceptionally precise clocks. Gravitational time dilation is vividly demonstrated in the vicinity of a black hole, where gravity is much stronger than on Earth. NASA has contemplated the scenario of placing a clock 10 kilometers away from a black hole with the mass of the Sun. From a safe distance, a telescope would reveal that the clock displays a difference of 1 hour after roughly an hour and 10 minutes. Another intriguing consequence of time dilation is the twin paradox. In this hypothetical experiment, two identical twins are involved. One remains on Earth while the other travels to a distant star at near light speeds. Upon reuniting later, the traveling twin has aged significantly less than the twin who stayed on Earth, owing to special relativistic time dilation. The paradox arises from the mistaken assumption of symmetrical conditions. Although it might seem that the traveling twin is stationary relative to the earthbound twin, leading to the belief that the earthling would have aged less, this is not the case due to the lack of symmetry in the situation. Special relativity refers to relative motion as motion in a straight line at a constant speed, which is not applicable in this scenario. As the twins start and end the journey together, the traveling twin must undergo phases of acceleration, deceleration, and change in direction. These factors introduce elements of general relativity, similar to the effects of a gravitational field. When accounting for this acceleration, calculations reveal that the spacefaring twin indeed ages more slowly than the earthbound twin, resembling a sort of time dilation effect.